Greetings, and for this materials science video we will be looking at the concept of linear density in the context of a body-centered cubic, or BCC, crystal structure. Now, linear density is defined as the number of atoms that one traverses divided by the distance traversed. Now, this linear density is going to be different based on the directions one could go within the crystal lattice. So a cube set up like this, and I've got one back here, and these are the cell edges. It should be straighter. There we go. Okay, and the body-centered cubic cell has one atom on each corner plus another one. I'm going to put it in purple in the middle of the box. So that's why it's referred to as body-centered cubic. Now, to characterize this linear density, the number of atoms divided by distance, we need to know and understand the geometry of what's going on here. I'm going to start with the distance. The edge length is referred to as A. Since it's a cube, that's A, and that's A, and that's A. In order to find the distances, we're going to look at three different directions. One is this direction. Since it's only going in the X direction and not in the Y direction or the Z direction, this is the 1, 0, 0 direction. Coming out here, we have 1 unit in X and 1 unit in Y. So this is the 1, 1, 0 direction. 0 because it does not go any direction in the Z. Coming up here, it goes 1 unit in X, 1 unit in Y, 1 unit in Z. This is the 1, 1, 1 direction. If you'll notice, it goes from the corner, the origin, through the central atom, out through the corner that is up and to the right and closest to the screen. Now, this is all difficult to draw on a 2D screen, so let's go down to a 3D model. Here we have the base of the red atoms. There's the body-centered one, the green, and then the upper layer is the blue atoms. Now these are all the same atom. The only difference is the colors indicate the levels. So you've got the red level, the green level, and the blue level. Right here, this arrow is the 1, 0, 0 arrow, only going in the X. Here's the 1, 1, 0 direction, going in both X and Y. And this up here is the 1, 1, 1 direction, going in X, Y, and Z. Notice how this is the only one that hits the atom in the middle. Now, these are not representative of the atoms in what one would call a full sphere form. If they were in full sphere, then these three atoms would be touching right about here in a tangent manner on their spheres. The red atoms would not be touching. There would still be a space here. The blue atoms would not be touching, and the red and blue atoms would not be touching. Anything along the cell edges would not touch. Just the ones in this direction, or this family of directions. So these three would touch, and these three would touch. Okay, going back to our calculations, we need to find the edge lengths. Because these three would touch, this direction, or this distance from this corner all the way up to the corner up here, the center of this sphere to the center of this sphere, we have to pass through 4 radii, 1 red, 2 green, and 1 blue radii. That's going to come into play when we do our calculations for our distances. So I am now going to draw just the bottom 4 on a square. So from the 3D model, these would be the red atoms. So I'll make them red. And again, the dimensions here are A and A. So this is a nice square. So we know, at least in terms of the cell edge length, what this distance is in the 1, 0, 0 direction. So this is the 1, 0, 0 direction, and this is the 1, 1, 0 direction. Well, we need to know the distance in the 1, 1, 0 direction, and that's easy enough to calculate. So we have a triangle here, right here, and one side is A, another side is A, and it's a right triangle. So we can use the Pythagorean theorem. A squared plus A squared equals, I call this just a nice hypotenuse H, H squared. So our distance H squared equals 2A squared. So H equals square root of 2 times A. And so this is our distance in terms of A for the 1, 1, 0 direction. A is our distance for the 1, 0, 0 direction. Now it's left just to find the distance in the 1, 1, 1 direction. This takes a little more geometry. So we are going to have another triangle, and it's going to start back here at the origin again, go all the way up to the center of this atom, come down to this atom, and go back. As we just determined, this distance here from corner to corner on the plane is h. This height here is a. So we'll make our triangle right here. With h along here and a. Well, h, as we found out, is square root of 2a. So square root of 2 times a. And let's find out what this is in terms of a. All we need to do is, again, square one side, add it to the square of another side. So the square root of 2a squared is simply 2 times a squared. And add them up together and we get 3a squared. Take the square root of this, and we end up with square root of 3 times a. But we need to find linear density in terms of the radius of the atoms. Well, as we figured out before, this distance from here to here along that 1, 1, 1 direction is 1, 2, 3, 4 atom radii long. So if I mark this right, this is in the 1, 1, 1 direction, and it is equal to 4 atom radii. So if square root of 3 times a equals 4r, then I can put a equal to 4 times r over the square root of 3. Of course, we already know that a is the length, the distance we need for the 1, 0, 0 direction right here. So we have that. 1, 0, 0 direction. And if we look at the 1, 1, 0 direction here, it's the square root of 2 times a. So square root of 2 times a equals the square root of 2 times 4r all over the square root of 3, which equals 4 times the square root of 2/3, all that times r. And that is our distance for the 1, 1, 0 direction. And as we already know, 4r is our distance for the 1, 1, 1 direction. Okay, well, that's the hard part. Let's put this into a table so it's a little better organized. So we have our direction, 0, 0, 1, 1, 0, 1, 1, 1. And we need our distance. And we have 4r over square root of 3. And then we've got 4 square root of 2/3 times r. And this one is simply 4r. Now we need to work on the number of atoms. Okay, this is a little bit easier to figure out. We'll go to our 3D model again. And along our 1, 1, 0 direction, we run into, well, one radius and then another radius. So we actually have traversed a total of, or an equivalent of, one atom. So 2 radiuses would be 1 diameter traversing 1 atom. Looking at the 1, 1, 0 direction, it's the same. We have 1 radius here and then 1 radius here. That's it, going from corner to corner. So this also is 1 atom. So we only have 1 atom here and 1 atom here. If we go to the 1, 1, 1 direction now, you'll see that we traverse 1 radius here, 2 radii here, and then another one here. So we've got 1, 2, 3, 4 radii, which we already talked about, and that is 2 diameters, which means that we've actually traversed 2 atoms. So we got 2 atoms here. And now we can have our linear density expression. So for this one, we just take the number of atoms and divide by the distance. So we just take the inverse of this. So our linear density is square root of 3 over 4r. And the same thing here. Take this and divide it by this. So we'd have this as a reciprocal of that. So I'm going to take square root of 3 over 4 times the square root of 2 times r. And then this is much easier to work with because we just have 2 divided by 4, which is 1/2. So it's 1 over 2r. Now let's look up an example, say for the linear density of iron. Well, obviously we need to know which direction. We'll just calculate it for all 3. But iron is a BCC crystal under certain conditions, especially with regards to temperature. So we can punch up iron here in our favorite reference, Wikipedia, and we find that it is body-centered cubic most of the time, but face-centered cubic between 1185 and 1667 Kelvin. And also the atomic radius is 126 picometers, or 0.126 nanometers. Now, other references might have a different value for that, but it's not going to be that different. So we'll just move that out of the way. So for the linear density of iron, we will pull up our handy dandy calculator, take the square root of 3, divide by 4, we get 0.433. Then we will divide by the radius of iron, which, as we just figured out, is 0.126 nanometers. 0.126, and that yields 3.44, and our units here are going to be atoms per nanometer. And here we should have units of atoms, and the distance here is in the R. So we have 3.44 atoms per nanometer there. Then we'll do same thing, clear this, and take the square root of 3, divide by 4 times square root of 2, and that's what would be for any of the BCCs, and then divide by radius of the iron atom. We have 2.43. And finally, we can simply take 0.5, which is 1/2, and divide by 0.126. And we end up with 3.97 atoms per nanometer. Well, what's the point, and what does this mean? Well, that means as one would travel along a 100 direction, every nanometer you traveled, you'd hit about 3.5 atoms. And this way, you'd only be hitting about 2.5 atoms for every nanometer that you traveled. But going along the 111 direction, you'll hit a lot more. You'll hit almost 4 atoms for every nanometer that you travel. This means that this direction is actually loosely packed, so it's much more flexible. So in that direction, you could maybe pack some more atoms in, or it would be more likely to deform in a ductile manner, but less stiff. Whereas along this direction, there's basically no space, and it's much stiffer and maybe stronger or maybe more brittle, depending on the application. So this was a review of the definition of linear density and also of the geometry of a body-centered cubic cell. Calculated the distances in that cell with respect to the atomic radius. We created a table where we looked at each direction, looked at those distances, figured out how many atoms were traversed going along those distances in those directions, and then calculated it for a body-centered cubic cell of iron.